Welcome back to The Explainer. Today, we're diving into something that is absolutely fundamental to how our universe operates. But honestly, it holds this crazy hidden mystery that almost always goes completely unnoticed. We're talking about the thermodynamics of temperature, specifically thermal phase curves. We're going to decode the secret language of heating and cooling and figure out exactly what happens when matter transforms right in front of our eyes. All right, let's jump right in.
So here's a question for you. If you add heat to something, does its temperature always rise? I mean, it seems like total common sense, right? You put a pot of cold water on a hot stove, you crank up the burner, and boom, you expect the water to get hotter and hotter. Heat equals a temperature increase. It's just an everyday assumption we all make. But as you'll see, the physical world loves to throw us curveballs. There are these crucial moments where you can literally pump massive amounts of heat into a substance, and its temperature will absolutely refuse to budge. No way, right? Well, to solve this mystery, we got to look at the data.
To wrap our heads around this, we use what's called a thermal phase curve. Basically, this maps out temperature against time, tracking the journey of matter as heat is either added or taken away. It's like a literal roadmap of physical transformation. We aren't just staring at boring numbers here, we're tracking the entire thermodynamic life cycle of a substance. Let's see how this actually builds.
Section 1. The heating curve. The journey from ice to steam.
Okay, imagine you're adding continuous heat to a solid block of ice. At first, the kinetic energy spikes, the particles start vibrating faster, and the temperature climbs right up. But then, right at 0 degrees Celsius, we hit a brick wall. The temperature just flatlines. Even as we keep pouring heat in, it stalls out until every single ice crystal becomes liquid. Once it's all water, okay, the temperature rockets up again until we hit 100 degrees. And that is where we hit our second mysterious plateau as the liquid vaporizes into steam. Only when every last drop has turned into gas does the temperature finally start climbing again.
The contrast on this graph is pretty striking, isn't it? The sloped lines make sense. That's climbing kinetic energy, particles moving faster. But those flat horizontal lines, that's where the physics gets completely wild. The temperature is just stubbornly locked in place. You could literally be blasting it with a blowtorch and the thermometer won't budge a single degree. Here's a crazy fact. It takes as much energy to simply melt a handful of ice at 0 degrees as it does to heat that exact same resulting puddle of water all the way up to 80 degrees Celsius. The heat is definitely going somewhere, but it's completely hidden from our thermometers.
Section 2. The big reveal. Why are there flat lines?
Well, the culprit here is latent heat. And latent literally translates to hidden. During those flat lines, the energy isn't actually raising the temperature at all, it's being hijacked. You see, it takes a massive amount of thermodynamic effort to physically rip apart the intermolecular bonds of a solid or a liquid. So the heat hasn't vanished, it's just busy doing the heavy lifting of structural transformation. For water, the latent heat of vaporization is exceptionally high because of those intense hydrogen bonds holding the molecules so tightly together.
So, behind the scenes, this is really a tug of war between kinetic and potential energy. On the flat line, kinetic energy, which is the motion we measure as temperature, is basically put on pause. All that incoming heat is being pumped straight into potential energy instead, fundamentally rearranging the molecular architecture. The heat is altering the arrangement of the particles, changing the actual state of the matter from a solid to a liquid or a liquid to a gas. It's only when that state change is 100% complete that the added heat goes back to raising the kinetic energy.
All right, moving on to Section 3, the cooling curve, reversing the process. Now, what if we run the tape in reverse? If we start removing heat, the descent totally mirrors the climb. A cooling gas drops in temperature until it condenses, plateauing as it turns back into a liquid. Then, the liquid cools and hits another dead stop at the freezing point. The rules of thermodynamics demand these exact same pauses, whether we're building molecular bonds or breaking them apart. The entire descent is governed by the exact same physical rules as the ascent.
Just like on the way up, they hit those stubborn flat lines during condensation and freezing. Even as the environment is desperately trying to cool the substance down, latent heat is actually being dumped back into the surroundings as those bonds reform. And hey, this massive release of hidden energy is exactly why a steam burn is far more damaging than a boiling water burn. When steam hits your skin and condenses, it isn't just hot, it is aggressively dumping all of that stored up latent heat directly onto you as it shifts back into a liquid state. Pretty intense, right?
Section 4. Key terms and final summary. Let's decode the graph.
Okay, so we've covered the core transformations: melting, boiling, freezing, and condensation. But the absolute linchpin connecting all of this together is latent heat. It is the hidden energy driving those state changes at a constant temperature. Once you connect these vocabulary words directly to the physical changes, reading any thermal phase curve becomes incredibly intuitive. It lets you instantly understand exactly what the molecules are doing at any given moment.
If we want to distill the whole shebang down to a super simple rule for reading any phase curve, it's this. Slanted lines mean temperature is actively changing, flat lines mean the physical state is actively changing. It really is that straightforward. Whenever you see a slope, you know the heat energy is affecting the kinetic energy. But the moment you hit a plateau, boom, you know a major structural transformation is taking place. The temperature takes a breather, and the state of matter shifts.
So, to sum it all up, heating curves climb and cooling curves fall, but it's really the plateaus that tell the most fascinating story. Just remember that kinetic energy rules the slopes, actively moving the thermometer up and down, but potential energy completely dominates those flat lines, quietly doing all the heavy structural lifting behind the scenes. Grasping these dynamics, that gives you absolute mastery over thermal phase curves.
We started this explainer by asking if adding heat always raises the temperature, and we ended up discovering the hidden, awesome power of latent heat. Think about it, energy that is entirely devoted to breaking atomic bonds and completely restructuring matter, all while our thermometers just sit perfectly still. It kind of makes you look at a simple pot of boiling water with total awe, doesn't it? It really makes you wonder if latent heat is powerful enough to hide massive amounts of energy in plain sight. What other invisible physical battles are happening right in front of us every single day? Keep questioning the world around you, keep looking closely at the data, and I'll catch you in the next explainer.